Hey, I'm Alex.
I'm Brian.
My name's Logan, and this is our digital filter project.
To start coding the microcontroller, pins for the sound input and red and blue output must be initialized. As seen in the code, the analog input for the sound input was assigned to PTB2, and the PWM outs for red and blue were assigned to pins PTA4 and PTA5 respectively. PWM out must be used to vary the duty cycle of the output, consequently allowing brightness control. Then the low pass and high pass variable were declared to be used later. Within the main method, an infinite while loop was created to run the low and high pass code within it continuously. The low pass filter used an average formula to get a numerical representation of the frequency using the data taken from the sound input as stored in the X array. A recursive method was used to incorporate the previous Y low pass into the average formula to help make this a more accurate reading for the calculation. Then, if Y low pass was above 0.8 or below 0.0025, then the blue output was assigned to Y low pass, and otherwise the blue was turned off. The high-pass filter used the difference formula to get a numerical representation of the frequency. It also used a recursive method to compare the current difference to a previous difference to get a more accurate reading. An if statement was used to make sure it's a positive value, and this difference was used within the if statements to turn on the red if the difference was greater than 0.3, and otherwise the red was turned off. Then the X array is updated.
If the output of the speaker was wired straight to the microcontroller, it would prove difficult to sample correctly due to the audio signal being generated in millivolts. To counter this, the output was routed through an operational amplifier with a gain that would provide a large enough voltage for the microcontroller to sample accurately, but not so large as to damage it. This was accomplished using both a 470 ohm and a 5.1 k ohm resistor in series, wired as a voltage divider back to the inverting input, pin 3. This provided a maximum output of around 2 volts and greatly improved the performance and accuracy of the system reacting to the correct frequencies.
Based upon what we learned from our theory, we take the audio source and feed it into an op-amp, which is being used as a gain function. This is to boost the signal before heading into the analog input part of our microcontroller. Within the microcontroller, we run our code, and depending on where the frequency lies on the hertz band, the signal leaving out of digital outputs will pass into a transistor, which will then feed the signal directly to LED strips that will illuminate on the acrylic panels. In conclusion, we use an audio signal that was boosted through the use of a gain op-amp to then feed a signal into a microcontroller that was used to create the digital filter. Using an average function recursively, we created the low-pass filter along with the difference function that was used recursively to make the high-pass filter. This code analyzes the signal and sends it to a separate and appropriate LED strip. This project could have been improved with the use of a more accurate low and high-pass filter as well as improved parameters.